Hello everyone. So today we are going to discuss another modulation technique which is called as color shift keying or also called as CSK. Uh, Actually, if you see the LEDs which are used in optical wireless communication for indoor communication, they are basically two types. One of them is you have basically a blue LED, and then there is a phosphorus layer on top of it. So this actually gives you white light. But the issue with this is that it has a very slow relaxation time, or it slows down the response. If I want to modulate this LED, because of this phosphorus, it will slow down the response. So basically such LEDs which are combination of blue LED with phosphorus coating, they are not an ideal candidate for modulation because they limit the response. The response of the signal is limited. The other type of LED is RGB LED, which is, it is basically, there are three LEDs inside. One is red LED and green LED and blue LED, and when it gets combined, it gives you a white light. So both of them give white light, but the response is not limited because there is no phosphorus layer here. So you can separately modulate the red light, you can separately modulate the green light as well as blue light, and basically there is an increase in terms of data rate if using if you are using WDM technique, because you have three colors here and there is no limitation coming, because unlike in blue LED with phosphorus coated. So why the CSK schemes actually makes use of will use RGB as the LED. So this is listed also, or this is discussed, or this is also a standard in VLC optical wireless communication standards, which is IEEE 802.15.7. It discusses about color shift keying as one of the modulation technique for indoor communication or outdoor communication as well. So this is discussed in Phi 3 layer, Phi 3 layer. So before we understand this CSK, let us understand about a color diagram which will explain how different colors can be used for communication. So as we know, every visible color can be reproduced by mixing three basic colors. So if you have red color, the green color and the blue color, you can basically generate any kind of color. And here I have given the values of the wavelength for red it is 700 nanometer, for green it is 546.1 nanometer, and for blue is 435.8 nanometers. And this is a curve of luminous efficiency, curve of human eye, and this standard is actually called as CIE 1931. So this is shown for two regions, that is photopic regions and scotopic region. So this is basically when you have enough light, which is actually photopic region, and when you have less light, or the light is not in high intensity, then it is scotopic region. So this is the response or the luminous efficiency curve of the human eye for two different regions, which is also represented as V lambda. So this is efficiency curve versus lambda, which is called as V lambda. And these are the color matching function. These are the color matching function, and in this diagram if you see there are two color matching function, two curves are given. One correspond to 1931, the other is 1978. So both are part of the standards, but 1931 is the official standard, is the current official standard which is followed. So we will focus our discussion only for 1931, CI 1931. So these are the color matching function x bar, y bar, z bar. So for blue, this is the, for blue it is z bar, and then you have for the red it is x bar, and for the green it is y bar. So this is the wavelength versus color matching function for different colors, x bar, y bar and z bar. So these are the color matching function. And how you can translate any color to some chromaticity coordinates. So this is what this particular slide explains. So you have tri-stimulus values, which is capital X, capital Y, capital Z, and this is some constant, and this is this is the spectral distribution, power spectral distribution. This is power spectral distribution of the light, and this is the color matching function, CMF. So this power spectral distribution is weighted with the color matching function, corresponding color matching function. You get the value of capital X, which is the tri-stimulus value. Similarly, you can calculate capital Y and Z. And if you want to convert this into some coordinates x, y, z, so x is given by capital X divided by this is the total, this is the total, again the total, and similarly for z. Now we see from here the sum of these chromaticity coordinates x and y. This is x, y, z. If you see, it is 1. So even if I know x and y, the z can be found out. So basically I need only two values, the third can be found out because the sum of these chromaticity coordinate is 1, x plus y plus z is equal to 1. And this is the transformation which is used. This is the capital X tri-stimulus value, and this is the RGB, and this is the matrix. So this is a transformation between x, y, z and RGB, and these x, y values are given here in terms of R, G and B. And if you see here in these equations, x plus y will be 1 minus z. So basically I need to calculate only x and y value, and I can map any color to xy coordinate using color matching function. So this is the diagram we get, which is called as chromaticity diagram. So you see on this coordinate is x coordinate and this is y coordinate, and the diagram looks like this. So at the top you will see some specific wavelengths, 5 to 20 nanometer or 70 nanometer or 450 nanometer, and there are other wavelengths, they're denoted by these dots here. And I mean, if you want to choose any color, for example this color, then the corresponding value of x will be this. So any color can be written or explained or shown in terms of these xy coordinates. And if you see in the middle, for example this area, this gives you different tones of white light, because here the contribution of red, green and blue, they are all the colors are present, and when they combine they give you a white tone. So this particular thing, which is 1 by 3 x value, 1 by 3, and the z will be 1 by 3 because the sum has to be 1, gives you this particular coordinate, and this has some value of x and some value of y. So this is this has value of x is 0.33, 0.33 and 0.33, and it gives a white tone if you have this particular point. So this is chromaticity diagram, which explains that any color can be written in the form of some xy coordinates. So standards have defined these 7 bands. So this is the 7, these are the different bands here, and they are given by some code 000, 001 and so on and so forth. And if you see the center wavelength, it is given by here, that is the center wavelength of this band 380 to 478 is 429. And if you see the corresponding xy coordinate is given here 0.169 and 0.007. So the standards have defined these 7 bands. And now let us let us now make how a TSK transmitter, CSK transmitter will be designed. So you have a data here, and normally the data may have continuous run of zeros and or ones. So normally you scramble the data before giving to further processing. So this could be some kind of scrambler. And then we have the standard channel encoder. And then we do the color coding. And it will give you some value corresponding to that particular color in terms of x and y. And then this x and y will give different power or different intensity, which different power and intensity or power, which are referred for different LEDs, which are red, green and blue. So XY to PI, PJ and PK. So this is the intensity, this is the power which is to be given to different LEDs. So this is the LED I, this is LED, this is LED J and K. So these are actually optical sources or LED, and this is the power which is transmitted. So this is how a typical CSK transmitter works. And the best thing is that there may be a different value of PI, PJ and PK corresponding to these two XY values. But if you see the total value, the sum will remain the same. So the PT will remain as same. So basically you will not notice any flicker coming here, because the power is constant, only the relative power is changing. So there is a zero flicker. Now let us understand how do we make constellation diagram in CSK. We have read about constellation diagrams in RF, where we have, for example, this is BPSK, there is one here, this is a plus A, this is minus A, and also QPSK. Or you can have 16 QAM, this is 4 here, this is 4 here, this is 4, this is 4, this is 4. So this is what we have studied in any digital communication or in RF domain. So let us see how we can design a constellation diagram for optical wireless communication system. So suppose I want to design for 4 CSK, for example. So this probably one point can be here, the other point can be here, this point can be here, I mean inside that CI 193 diagram. And the 4th point could be in the middle. So this is say K, this is IJK, this is I, this is J, and this is say S0, S1, S2, S3, and they all represent some data symbols. So, for example, 00 will correspond to say S0, and say 11 will correspond to say S3. So, there are various algorithms which have been designed, and for designing such algorithm one has to consider few things in mind, that you should be able to design algorithm for any size, or whether it is 16 CSK or 64 CSK, and the algorithm should be such that ultimate light which comes out is white. So, there are some white constraints you have to maintain. And also you have to design these constellation points in such a way that the distance between two adjacent constellation point is maximized. So, maximize the Euclidean distance. And also, because you are transmitting 3 colors, so you have to also see that the crosstalk among these colors is also minimized. So, one has to also consider the crosstalk among different colors. So, designing any constellation size for optical wireless communication will require all these constraints which have to be tackled. Crosstalk among different colors. So, this is example of 4 CSK, and 8 CSK, for example, I want to design a 8 CSK. So, this is a middle part, this is a middle part. So, one point could be this, I am representing each constellation point by a cross here, could be this, and this is another point, and one point can be somewhere here, and another point could be this. So, there are 8 such points. So, this is they represent for example 000 to 111. So, this is 8 CSK, and if I want to design a 16 CSK, probably I can consider something like this, but there are other algorithms which can give you much better results. So, this will be, this is for 16 CSK. So, this is one. So, these are the constellation points. This is in this diagram, constellation. So, there will be one here, one in the middle, so this could be a constellation diagram for a 16 CSK. So, let us now draw the complete block diagram of CSK system, including the receiver. So, this will be the data. So, I am skipping the scrambler and then source encoder. Those are standard blocks which you have in a CSK system. This is color coder, and it is mapped to some XY values, and this is XY to RGB, which is given by that transformation matrix which we had discussed when we were discussing about CI 1931. So, this will give me a PI, PJ and PK. So, this is given to red LED, red, and this is blue, and this is green. And then you have the PDs here with filters. So, this PD is PD with the red filter, and the PD with the middle one is PD with blue filter, and the last one is photodiode with green filter. And when the light is getting transmitted, it should be sensed by this photodiode ideally, but it may go here as well, which is actually the crosstalk may go here, and similarly the light ideally should go here, but it goes here. So, these are the interference here. Similarly for green. So, actually you will have a matrix here, channel matrix, and these are the interference, these dashed lines, they are the interference. So, once you have this, and then after the PD, that noise which is say for PI is NI, this gets added, and then the power is say PI dash, and similarly the noise, this is NJ, and the power is PJ dash, and similarly NK, power is PK dash, and then these powers are given to RGB to XY mapping. And once you have got these XY, from here you can use color decoder. This is was color coder, color decoder, and you get your data from here. So, this is a complete block diagram of CSK system. Also, we had discussed about these bands in this table. These are different bands defined, 7 of them, which are represented by codes, and their central wavelength is this, and these are the XY coordinate. Now, so you can have, when you are transmitting your CSK signal, you can have some combination of these color bands. So, for example, for band I, band J, you can have combination of, for example, 110 is somewhere here, or 010 somewhere here, and 000 is somewhere here. So, you can have different combinations. So, the standards, they have defined some 9 combinations. So, in total there are 9 such combinations. So, here, and they all differ in terms of constellation, constellation diagram, and also the minimum Euclidean distance also varies for different combinations. So, this particular plot actually gives a shows the Euclidean distance for different constellation size and for different color band combinations. So, CBC stands for color band combinations. This is CBC. So, for example, CBC1, this particular one is represented by this color. This is CBC1, And if you see, for example, this one, the last one, which is CBC2, this is CBC2. So the minimum Euclidean distance, for example, for CBC7 is for 4, the values are less as compared to CBC1 or CBC2. And if you see for higher, the same trend is valid for higher constellation diagram. So basically, this will give you different performance in terms of, BR. So one can try, different color band combinations, and you will get different minimum Euclidean distance, which will actually decide what is the performance of your system. Now let us understand about the channel model. So channel model, let us see, we have a set and represent by P1 to PM, and this is for say MCSK. So these are the constellation points from P1 to PM, and each P1 is represented by a set of colors. So each P1, let me write as Pi, which is actually a vector now, is represented by some red color, some blue color, green color, blue color. And the receipt vector R will be represented by RR, RG and RB. So this is the receipt vector. And receipt vector can be written as the channel matrix H, which will be a 3 cross 3 matrix in case of 3 colors RGB, H into responsivity into P vector plus N vector. This is a noise. And noise will be for different colors. It will be a set which is NR, NG and NB for different colors. So for the sake of simplicity, I can take H is equal to 1, the gain is 1, and also assume that there is no crosstalk between among the colors. So H can be taken as 1, and let us assume also responsivity as 1. So basically the receipt vector R will be P plus N. And these noise are AWGN, treated as AWGN, and they are IIDs. So this is the receipt vector. So this is how the channel model is represented. Now let us try to understand the constraints and what is the detection mechanism which we use. So the constraint will be these different colors, that is PR, PG and PB. They are either 0, greater than or equal to 0. It cannot be non-negative. It can't be negative. So, and the total power is actually sum of these powers. So the relative power is changing, but the sum remains the same. So that is why we discussed earlier that there is no zero flicker, there is no flicker, because the output power remains the constant. And so the total color of illumination will be white if you combine all these colors. So you will get white. And this basically one has to ensure that that is I is equal to 1 to m pi should give power which is corresponding to white, PW. And for detection, we use maximum likelihood receiver or MLRX, which shows that the estimated value P, and this will be vector, estimate value will be argument. Suppose R is the receipt vector, this should be minimum, that is this Euclidean norm R minus Pi should be minimum. So this is the Euclidean norm. And this is for all values belonging to that set, which is actually curly A. And remember, this A was P1 to Pm. So the power actually is proportional to I. The power which is falling onto the photodetector will give some corresponding current which is proportional to the incident power. And if I calculate the electrical power, it will be basically I square by R. R is a load resistance. So it will be square of the current, that will be the electrical power. So if I write electrical power, which is say S, electrical power, that will be proportional to the square of the power in red, blue and green. So S will be proportional to PR square, sorry, not PR, PR red, PG square plus PB square. There is a total power. So the SNR for such a system is defined as gamma, which is PT square, the total power square, because I'm considering the electrical power, and the noise is basically coming from all the sources. So this is sometimes called as CDO SNR, as if only one photodiode is there. So the equivalent noise which will come from different sources will be actually N0 plus N0 for different colors plus N0. So this is represented as PT square over 3N0. So this is the gamma or the CDO SNR for such a system. Now try to, in order to calculate probability of error for such a system, we need to understand the concept of CSK signal space. So in CSK signal space, suppose I represent those three colors by three coordinates. So this is a PG, this is PB, and this is PR. And let us see, this is the total point PT. This is PT because we know PT is equal to PB plus P power in the red or power in the green. So this point actually the power, total power is in PG, so this is, others are 0, so this will be PT here, similarly this will be PT here. Now I want to, this is a 3D CSK signal space, so I want to convert this 3D into 2D, then I'll do some transformation, and this will be basically x and y, and this point, so this is your x, this is y, so this is, I'm trying to convert this 3D into 2D. So let us represent pi vector, each component here as a 3D constellation point. So P will be I mean Px or Py, Pz, say, and similarly R will be, I mean these XYZ are actually for red, blue and green, so I'm writing in terms of XYZ. So this will be Rx, Ry or Rz, and noise NZ. So if I convert this into 2D, it will be represented by XY coordinates, 2 coordinates. So which I represent for PD, for 2D, I am representing P with a line here. This is different from 3D where I show an arrow here. So this is 3D. So P for 2D system will be Px, Py, similarly R will be Rx or Ry, and N will be Nx and Y. So if I do this transformation from 3D to 2D, I'll get something like this. So, and these points are 0, root 6 by 3 pt, and this particular point will be root 2 over 2 pt, root 6 over 6, and this is minus pt, and this point will be minus root 2 to 2 pt, minus root 6 to 6 pt. So these are the points I will get when I map this 3D system to 2D systems, and this is actually done by a transformation matrix, and in this case the transformation matrix T will be one by root 2, 1 by root 2, 0, minus 1 by root 6, and this is 2 by root 6. This is the transformation matrix. That is P 2D with single line is T, this is the matrix, into P, which is a 3D constellation point. So similarly for you have R, and similarly for N. So this is the transformation I have done from 2D space to, from 3D to 2D. So I have got 2D symbol sets, which is A. I represent this like this. So this will be P1, this is 2D, so on and so forth, PM. This is the mth constellation point, this is 2D. So this is the 2D symbol set I have got from that 3D which had red, blue and green. So now let us try to do the SCR analysis, symbol error rate analysis for a CSK system. Symbol error rate analysis. So for doing this symbol rate analysis, let us draw a 2D constellation diagram and try to understand the decision regions. So let me again draw this. So this is a 1 point, let me call it as a P1 here. This is the 2D point P1. This is, let us just say, P3, and this is P4, and this is P2. Now, what is the decision region for different points? So for P1, this is the decision region which is inside the triangle. So this is the decision region points, the decision region rather, for P1. And similarly, we can find out the decision region for other 2 points. So let us for that we'll have to draw a triangle which is so for the decision region for P2, for example, will be, this is a single line here, so I have drawn 2 lines here. So for decision region for P2 will be actually this which I am showing as shaded. And inside this is the decision for P2. Similarly, there is a decision region for P2, P4 here, and similarly for P3 here. So any point which is falling in these decision regions will be estimated as that particular constellation point. So if your point is falling, say for example somewhere here, it will be, and the detected point or the estimated point will be P1 bar, and if your point is falling somewhere here in this decision region, then it will be P2 bar, or similarly for P3 bar or P4 bar. So let us write now as Pn, where n is 1, 2, 3, 4, 2 dimension is the error probability for constellation point Pn. So P4 PSK, which is a probability of SCR. This is a probability of SCR for 4 PSK will be given by 1 by 4 summation of all these probabilities. There is P1 plus capital P, so P2. So this is the constellation point. This is the probability P. So this will be sum of these and divided by 4. That will be the probability of SCR. And if you see the decision region here, that is 2, 3 and 4, 2 for corresponding to P2 bar, P3 bar and P4 bar, that decision region is identical. It is same. So that probability will remain the same. So P2 is equal to P3 is equal to P4. And so probability P1 of P1 bar is we need to find out, and we need to find out any one of these probability. Since they are all equal, so I need to only find out PP1 and PP2, and then I'll be able to calculate P4 PSK. And if you notice this PP1, actually let me draw another diagram to explain about this PP1. So this will be so this is say this is the region say 1, this is the region say 3, and this region is 2. So PP1 is given by, and this is for say P1, this is P1. So if the point which was actually P1, the transmitted was P1, and it has fallen onto either 1 or 2 or 3, that is in error, right? It should have been estimated as P1 bar, but it is falling in one of these regions. So the total error probability will be PP1 will be given by the probability of error falling in 1, falling in 2, falling in 3, so which are represented by this PE1, PE2 plus PE3. And to understand this PP2, this we have discussed about the P1 part. Let us now discuss about the P1 part. So for that, let me draw another diagram here. Maybe in this space, let me draw here. So this I'm drawing this particular region, that is a P2 region I'm drawing, or we can see I'm just drawing another P2 region here. So this P2 region will be something like this. Just concentrate on the P2 region. P2 region will be so this is the P2 region. This one is the P2 region. I have redrawn here just to make it more clear. And I have additional, I denote this as say 5 and I denote this as 4. And this region is say 4 here. Sorry, this region is, this is 6, this is 4, this is 6. Right. Then for PP2, this is P2 will be if the point falls either in 4 or 5 here, or this is 6, then it will be in error. So PP2 will be PE4 plus PE5 plus PE6. So PP1 was when the point is falling in other places which are P1, P2, P3 denoted here. Then these are the probability of error for P1, and then probability of error for P2 is if the point is falling in not in P2 but any region which is 4, 5 and 6 in this diagram. So these are the two probabilities we have. So now I can put this value, this PP1 and PP2 in this equation. Let me name this as A. And when I put this equation and I use these identities, that is PP1 is equal to PP3 is equal to P4, and also I know that PP4 5, so sorry, this is 5, is equal to P6. So this region 6 and 5 here, this one and this one, 5 and 6, they are same. So using all these identities, we can calculate what is P4 CSK. So this we know, and this is also equal to PE5 is equal to PE6. So this will give Phi4 CSK. Basically, I'll put all these quantities in my earlier equation which was named as A. So I will get 1 by 4, 6 PE1 plus 6 PE2. Now I need to calculate PE1 and PE2 to get the total probability of error. So how do we calculate PE1 and PE5? So for calculating PE1 and PE5, let me draw a decision region of the form which is equal to PE5 and PE1, and then we can calculate the values of PE1 and PE5. So it is something like this. If you carefully see, the decision regions are, so this is a Pn point, and this is a X, this is O, let me write this as psi, and this is say xi, and this, suppose receipt point is somewhere here R, right, and then this makes with the Pn this, and this distance up to this point is say R, this is R. So this, if you see, this is a region equivalent to P5. It will have some value of psi and xi, but this is equal to 5. So we'll put the limits of psi and xi and try to calculate this 6PE1 and 6PE5. So for calculating this probability of error, because this R can be anywhere, it can be from R to R to infinity. If it is in this region, in the region which is in this region here, the region which is shown here, then it is not in error. But if it is R changes from R to any other point infinity, it is in error, right? So these limits are from R to infinity, and this is angles are 0 to xi. This xi can change from 0 to some angle xi, and this is the distribution which is Gaussian distribution, which is given in polar coordinates. So this is bivariate. I mean, this is the distribution which R will have. So bivariate Gaussian distribution in polar coordinates. So this is given by this equation, the probability of error. And when I calculate for PE1, PE2, the values of psi and x and xi, they'll be different. So we'll put those different values in order to calculate P1 and P5. And as you see from this diagram, psi is equal to pi minus xi is equal to pi minus psi, and Fr theta is actually that bivariate Gaussian distribution in polar coordinates, which is represented by r divided by 2 pi sigma square exponential minus r square by 2 sigma square. So, putting these values and using this law of cosines, this is law of cosine, and putting the values here, then I can get that expression for P is equal to 1 by pi 0 to xi exponential and given whatever is given in the bracket into d theta. Now, for 4 CSK, these are the values of xi's, psi's and xi's. So, I is equal to 1, this is P1, we will calculate. Xi is given as root 6 by 3 pt, psi I is pi by 6, xi is 2 pi by 3. Similarly, for calculating P5, for I is equal to 5, these are the values of xi and psi. So, putting these values in that expression, we get P4 probability for P4 CSK, which is given by 0 to psi 1, and this is corresponding to 2 pi by 3, and this xi 1 is corresponding to 2 by 3, and this xi 1 is corresponding to pi by 6, and similarly for I is equal to 5, and this is I is equal to 1. So, this is a P4 is PSK probability of error. Now, whole thing can be written in terms of gamma, and gamma, remember, it was Pt square divided by 3n naught, where Pt square is x1 square. So, you can replace this x1 square and sigma square with the corresponding gamma value. This is the gamma value we have introduced. So, this is the probability of error expression for P4 PCSK.